Welcome to this Introduction to Computer Vision for Renaissance Book and Art History, a workshop for the Renaissance Society of America's Day of Digital Learning 2020, originally scheduled for 5th of April in Philadelphia. I'm instead making this recording in Oxford on 23rd of April. My name is Charles Burgle. I'm a book historian and a digital humanist based in the Visual Geometry Group, Department of Engineering Science at the University of Oxford. I'm grateful to you all for joining me. I'm also grateful to Angular Dressen in particular for organising this event as part of the, on behalf of the Day of Digital Learning on behalf of the RSA. Here's the agenda for today's workshop. I'm going to start by giving an overview of computer vision tasks and methods before going on to demonstrate some of the software tools that my group, VGG, has created to address those tasks and implement those methods. Then I'm going to provide you with materials by which you can try out the software itself using either online demos or user installable software. So here we are in the workshop, part 1, overview. Always good to start with definitions. What is computer vision? According to Wikipedia, computer vision is gaining high-level understanding from digital images. What is meant by high-level understanding? A humanist will, of course, immediately say, and that kind of critical and contextual lens that the humanities brings to our field is very valuable. I think in general what is meant by high-level understanding is some kind of semantic or even human-like understanding of digital images, something more nuanced and meaningful than simply a raw count of pixels or color values. It's perhaps easier to describe computer vision by example rather than precept. Common computer vision tasks include annotation and segmentation, isolating elements of images, elements that are meaningful for particular use cases or particular people or communities. Comparison, spotting, again, meaningful differences between images. Matching, finding out what images have in common. And classification, describing what is in an image, its content or subject. Perhaps the cutting edge of computer vision is represented by this last task here, the part of computer vision that seems most closest to so-called AI, artificial intelligence, of which computer vision has been a pioneer. This is my research group, VGG, Visual Geometry Group. We're a large general purpose research group doing all kinds of things in computer vision, sometimes audio-visual content as well. This is the project that occupies a lot of my time within VGG, Cyberbyte, which is a research project with 2 objectives, as you can see. Its one objective is to carry out fundamental research, unsurprising for a research project. I won't go through the entirety of this text, but notice below an important objective is to transfer these methods to industry and to other academic disciplines. Specifically, my role within the project then is to disseminate the research arising from the project to appropriate communities in the humanities, and also actually in the cultural heritage sector. But importantly, part of my role is also to bring back research questions, interesting data sets, ideas for new development, bug reports, feature requests, etc. As an engineering group, as an engineering project, VGG is very interested in doing research and producing solutions that implement the research that perform well in the world, that fit real use cases, that work with real data on real live research questions. And I think that people in the humanities and the cultural heritage sector are perhaps unaware of the extent to which their research questions, and particularly their data, their well-curated, labeled training data, is of technical interest and of real value to computer vision researchers and technology firms. So this is why we engage with humanities and humanities research questions. Towards this end, VGG software has moved on in recent years from being implementing our methods in rather technical academic tools such as these here, towards some more descriptive and more general purpose and more easily deployable tools. So these tools here, these pieces of software, have perhaps more descriptive labels, image comparator, image annotator, and so forth. I'm going to talk about all these tools today and give you the opportunity to try them all, with the exception of VGG Face Finder, our facial recognition tool, perhaps less relevant for Renaissance studies, although it has been trialed and there's an active area of research, is facial recognition in art, as well as photographs and video. So these common computer vision tasks that I introduced, I'm going to go through each of them. Annotation and segmentation. Well, here is an annotation exercise with a view towards segmentation by machine. What you're looking at here is a page of a book, a 15th century page from a 15th century edition of Dante. This is part of a project envisioning Dante we're running in collaboration with Guider Armstrong at the University of Manchester. And this book page is surrounded by the user interface of our annotated tool VIA, which you saw on the previous one of the previous slides. VIA provides a user interface for marking up regions of the page with polygons and with arbitrary attributes. So you can define, tag or label, if you prefer, regions of the page. And normally the pipeline for this form of computer vision is to feed these annotations to a computer vision system, a machine learning system, normally using so-called deep learning. And from these labeled examples, see if the computer can learn some categories, some visual categories that are meaningful for a particular task. So here we're interested in things like the page as a whole, but also its sub-elements such as the commentary, the main text, the illustrations, ornaments, and even individual pieces of type, as you can maybe see round about here. Now, this is an example of so-called supervised machine learning, as I've suggested. It consists of feeding labeled information, therefore supervising the learning process, the machine learning process. We also want to try so-called unsupervised learning, a more advanced method in which you simply feed raw images, unlabeled images, to an image classifier and see if you can detect any latent patterns within the image. So this is an academic paper that some colleagues of mine in VGG have produced, showing the results of, for example, in the bottom of the image here, attempting to extract meaningful segments of this streetscape with no supervision at all. It'll be interesting to try that out with the book pages. Here's the software download page for VIA, the tool I showed the page in earlier. Like of all of our tools, it's entirely free and open source. You can do whatever you like with it under a so-called BSD license. We have versions of it for still pictures, for video and audio data, and it's widely used in machine learning pipelines. It's a very simple, it's not itself perhaps computer vision, but it's part of a computer, it can be incorporated into computer vision pipelines. Moving on, image comparison, spotting differences between images, something computers are very good at, perhaps better than most humans, certainly over a long period of time and a large amount of data. So a canonical form of difference spotting that will be well known to book historians of the Renaissance is spotting the difference in letterpress print. So here I've got a stage direction from 2 copies of Shakespeare's first folio works of 1623. And I'll give you 5 seconds to spot the difference between the top and the bottom example, which I've taken from the Folger Library's collation blog. Okay, time's up. You may have spotted that the I in the last word is inverted down here in the second of my examples, which is presumably printed first. This is presumably an uncorrected state of this page, corrected above. Perhaps this example is perhaps easy to see isolated from the surrounding page. But if one looks at the page as a whole, you can immediately see the nature of the problem. Again, this is Shakespeare's folio works. And the so-called Wimbledon method of image comparison, which is being demonstrated here, is actually inefficient. Spotting difference is hard. It's cognitively interesting how the brain, when making a comparison between two images, is swiftly overwhelmed by points of comparison. It's hard to hold those points of comparison in one's working memory while making the comparison. Now, to address this task, bibliographers have created a wonderful range of machines, optical devices over the years, so-called optical collators. Here are four of the most famous ones. Here at the back is the so-called Hinman collator, developed in the 1940s, which uses a pair of stroboscopic lights to swiftly illuminate two copies of a book and reflect superimpose the reflected light from each of them in a viewfinder. The other device is the McLeod collator, the Halley's Comet, which is the only one of these four I've used, and the Lindstrand comparator all use stereoscopy. They all permit the collator, the viewer, to view two copies of a book or a reproduction of a book at once, which are and independently, so one book per eye, one page per eye. These images are then overlaid in the minds, in the brain, in the because in the usual range of human vision, we superimpose, don't we, two separate streams of visual data to produce a single picture in the brain, and any differences will stand out, will almost flip-flop from one to the other. And ingenious technology, but as anyone who's ever used these will know, very hard, very exhausting, and perhaps even slightly injurious to your eyesight and your stamina over several hours. This can be. Now, to address this task, we've created software on behalf of the Oxford edition of the complete works of Thomas Traherne. It's called Traherne. It works by flip-flopping between two page images. So you can maybe see at the bottom of the page here, this catchword. Sorry about that. I'm going to go back so you can see that again. Do you see that? So a small variation. It's up to an editor to decide how meaningful it is. We simply provide the mechanism for seeing it in the first place. We also cope with the fact in Traherne that pages aren't always flat. So if you have two copies of a text that are variably bound, the geometry, the relative geometries of the two pages may be different and require rectification. So we provide a tool for warping those pages and aligning them so that any typographic differences can stand out. We've generalized this software as image comparator lately, so away from or including its original task in editing of text towards any kind of visual comparison. And that's available as an online demo, as most of our tools are in one form or another. Moving on, matching, finding out what images have in common. So this is a form of image recognition. The task here is to determine whether you are looking at images of the same object or not, perhaps from a different scale, as you can see here. A building in Oxford All Souls College shown in close-up and in long shot. This is in distinction from image classification, which I'll also talk about later in this presentation, where the task is to define the type of object that something is. In image matching, you're looking for the exact object or its analog, a close copy in the world, and asking if you're seeing the same object in different images. So we do this form of image recognition, which is also known as so-called instance-based image recognition through a so-called bag of visual words algorithm. You can see here these little red ellipsoids. These regions are being a match between two images, again of a building in Oxford, shown at different angles and at a slightly different scale. The term a bag of visual words is one that computer vision has borrowed from linguistics. Linguistics has actually produced lots of methods that have been profitably applied to images as well. And the analogy is that instead of treating, in linguistics, instead of treating texts as possessing high-level semantic structure, you simply view text as statistical aggregations of elements. So when we come to images, a bag of visual words consists of so-called local features, those little red ellipsoids I showed earlier, defined by differences in contrast. You get them, for example, at the boundary of objects, so an object silhouetted against the sky. These features are scale invariant. As you've seen, the size of images doesn't matter to some extent, to a large extent. They also survive rotation and skewing. So you saw that with my building that was viewed from different angles. It doesn't, however, survive any, they don't survive any geometrical transformations such as flipping or warping. Without modification, we can implement means of coping with that if necessary. The features are somewhat tolerant of changes in lighting. If an image is very low contrast, then it's harder to pick out these visual words, these geometric features. And matching is also fast, depending on the implementation. So here's a use case in Renaissance book history. Botanical printers' woodblocks currently held in the Plantin Moretus Museum in Antwerp, in Belgium. This was a research project carried out as part of an internship by Jesse Wei-San Chen at the University of Utrecht. And what Jesse did was take these images, which are offprints, relatively modern offprints of the museum's original 16th and 17th century woodblocks, which are still kept at the museum. But what she used were the offprints, which she had digital images of, and using our software, she was able to match the offprints, which were also key to the individual blocks, through a inventory number to their appearance in original Renaissance publications. Here's our instance matcher running also not as a private research tool, but an online service in two Oxford projects, Bodley and Ballads, which I'll demonstrate later in the presentation, and Christina Dondi's 15th Century Book Trade project. You can see here, in general, that the system has been able to match this woodcut in two copies of the same text, a broadside ballad, and similarly this illustration from an incunable present in two editions, one of which has been shaded partially, but nonetheless sufficient features survive to allow a match. Here's the download page and user guide for this software. Moving on now to image classification. As I've said, this is distinct from image matching. It's a more general form of image recognition. Now we do this with so-called deep learning. Deep doesn't necessarily mean profound, intelligent. Deep means a system in this context. Deep learning is a system that's composed of many layers, which provide increasingly abstract representations of an image, often culminating with some top-level description or label. So you can see here an image is generically transformed through various mathematical steps to become increasingly abstract. I won't go through what all these steps are, largely because I myself only have a very general understanding of how these systems work. That's step one then, is to feed large numbers of these images to a neural network, the innovation of which is that these systems are able to adjust the amount of the transformations that they make in order to provide the best fit with a desired output. So you would give, as I've shown with the Dante page, you give large numbers of labeled images to a neural network and tell it and try to encourage it to understand some features using only the image and a label as a guide, and it itself has the ability to adjust its own parameters to provide the most efficient mapping between that label and an image. Then step two, retrieval, might consist of taking the result of this training phase, a neural network represented well by a black box here, because notoriously after the systems have trained themselves, it's rather hard to figure out what features it's learned, although there's a lot of attention, a lot of research is going on to try to understand the internal representations that these neural networks learn from the images and their labels. But having been trained on lots of images, for retrieval purposes, we simply feed an image into the neural network, and then it returns a confidence score based on what it has previously seen on what it is now seeing. So we have a 0.97, 0.97, where 1 is a perfect, completely confident score that this is an image of a cat. Now, in practice, such systems are incorporated into pipelines like this. This is a collaboration we did with the organization Art UK, who mounts digital images of every painting in public ownership in the United Kingdom. And starting from the end of this pipeline, what you can see here, the system has retrieved images of men with beards from Art UK, so an unsorted collection of images, through a series of so-called CNNs, convolutional neural networks. So what we've done first of all is to feed all the contents of the Art UK resource, some 300,000 images, to a CNN through which it has learned certain features. That's in the back end, if you like. That's the server-side end. At the front end, the user interface, we've provided the ability for users to perform on-the-fly image classifications using images and keywords from Google. So the user has inputted the word beard, has on the fly retrieved some photographs of men with beards, which are again fed to a CNN from which a classifier is learnt. Also using, in this case, negative training examples. So in this case, we've given examples, things we're not looking for, to refine the classifier, which it has then applied to the so-called embeddings, the output of the CNN encoding of the Art UK resource, and has returned these results here. Software that performs this is called Vic. Like our other tools, it's free and open source. And we have instructions for how you can use it, and some demos for our flagship demo is audio-visual footage from BBC News, but we also have it publicly accessible over Art UK, and I have some demos using other data sets to show you as well. Now, this form of image recognition is perhaps rather naive compared to the kinds of compounded imagery that iconographers, art historians are used to working with, in which it is, of course, immediately recognizable for those who are at all familiar with Western art that we're looking at a nativity scene. We know it's a nativity because it is a compound image. It's a combination of stock elements, isn't it? Mary and a child, often an angel, perhaps shepherds, various forms of visual effects, lighting, and so forth. All these things can be decomposed from a scene and individually taught to computers, from which they might, this is really the cutting edge, I think, of computer vision art history, attempt to learn a rather high level classification than these simple labels such as cat or beard or dog. Excuse me. Similarly, it's an area of active research to try to get computers to learn more complex iconography, such as is embodied in the icon class form of classification. But it's perhaps a rather distant prospect that computers can recognize these crocodiles as depicted by medieval artists who had clearly never seen a crocodile. That, however, is the kind of critical lens that I think humanists can usefully bring to computer vision. Moving on now to the demonstration phase of the workshop, I'm going to move to my web browser before moving on to independent tryouts. Excuse me, I got ahead of myself there. Okay, here I am. So here I am in the workshop Google Drive. You'll see the slideshow that I've been presenting, along with a software installation guide that I pre-circulated in the run-up to DDL. There's also a worksheet which I'm going to go ahead and look at, and that'll provide instructions for how to follow this workshop yourselves, using either online demos or local installation of the software that I've just demonstrated. And here's the guide, here's the document that was previously circulated on how to install the software should you wish to use it on your own laptop or desktop computer. So there are 3 tasks as part of the tryout part of the workshop. Task 1, matching images with Vice. The online demo that I provided, or I provided several online demos, but if you like, the lead demo is so-called image match from Bodleian Ballads, which I alluded to earlier. So I'm going to go ahead and open that and show you the user interface for making a match in Vice on this data set. What I've got here is 916 images that look like this, scans of largely late 17th century broadside ballads held in the Bodleian Library in Oxford. I'm going to go ahead and select a ballad in the interface, and then using my cursor, I'm going to draw around a region of the ballad, a woodcut illustration, and when I press search, it will run that, it will submit that region as a query against an index of those 900 images as a whole. So I go ahead and do that, and retrieval, as you can see, is fast. So I retrieve things that, as I go down, seem to be pretty much what I'm looking for. I can go ahead and click on detailed matches and see a close-up of each woodcut on different sheets. And I can also, by ticking bot lines and regions, see the features, the so-called visual words that the system has learned. I also have the ability to choose a file or a URL to submit a query to the system from outside the images that have already been indexed. And if you go to the workshop folder, you'll see I provided a couple of items that you can try out in this demo. So if I go back to my worksheet, there are some other more detailed instructions on how to try out Vice in this resource. There is also a catalogue of ballad illustrations that I'm just going to quickly look at. Now, what this provides is a semantic overview of the contents of Bodleian ballads. These are keywords that have been actually human assigned, but everything else has been done by computer. So one classifier has automatically segmented the image to cut out the illustrations. We've then clustered the illustrations by similarity. So these three are clearly similar. However, the system has also learned to distinguish between images of derived from separate blocks. So if I go in and look at the example I searched on earlier in image match, if I click on that, these are all the impressions of this one block. However, the system has also just detected similar blocks and provides a tool for comparing them. If I move the mouse backwards and forwards, you can see these two images registered show that they are very close copies, but if I'll see this hair in particular on the side here, they are not identical. They're not printings off the same identical wood block. And there are one or two other things that this catalogue view provides, but you can see how perhaps how image recognition can be incorporated into a cataloguing system as well as a live search tool. Back to my worksheet, I provided a couple of other online demos. These are real projects. Ornamental from University College Dublin provides over 250,000 pages from early Iberian printed books, along with metadata for them. Now, if you want to try out the software yourself, if you want to try a local demo, there are some instructions here. And I provided demo data, which is here, this folder, device local data. And I'm going to go and look at, I'm going to show you just quickly what that looks like on your own system. If you've installed the software, which does require you jumping through a few hoops, you have to install the Docker environment, which I'm using in conjunction with Kitematic. Docker Container Manager is the Kitematic interface. I'm going to start a Vice instance from Kitematic, and here's a small test data set I've created earlier from the test data on the workshop drive. I load that engine, and you can see there are also some broadside ballads, the same as in Bodleian ballads, but I've included one or two other things as well. I've included book plates and binding stamps as well, from 17th century ornamented Cambridge bindings. I won't demonstrate this now in any detail, just to make the point that this is software that you can install with perhaps a little bit of effort on your own hardware and make your images searchable. Okay, I'm moving on now to Traherne, our image comparator tool. This is how you use Traherne. This is, although it's running on a web browser, the user interface is a web browser. It's running on my own laptop. You can see by the icon in my computer and my Mac dock at the bottom here. If I select Load Base, I'm going to go to the RSA folder and open imcomp Traherne data, which is also available on the workshop drive. Imcomp is the web-enabled version, is the web-hosted version of Traherne, which I provided a link to in the workshop sheet as well. Excuse me. So I need to load pairs of images. I need to load a base and a comp pair, which I'll do. I'll select all of these images. I'll load the comparison. So I've loaded about 7 or 8 pairs of images, which I can click through in this user interface. So here's the first folio page I showed earlier. I've also provided some before and after restoration images of the Ghent altarpiece, recently revealed after restoration. Here's another detail from the same set of images. And another. Here are 2 pages of a book that, as you can see, are skewed variably. So you can try out the compare curved book pages feature using that. Again, here's a detail of the same page in different copies represented differently, imaged differently. And here's an engraving. I'll just demonstrate. I'll use this example to demonstrate. As with Vice, I can draw a bounding box around a region I'd like to compare. I'm going to press the compare, and then it will extract regions that match between each image and overlay them. I can visualize the 2 overlaid pages in different ways. So base here just shows the cropped view of the base image. Overlap shows the 2 pages blend together with a degree of opacity. Composite is the blend. Diff is shows 1 image in blue and 1 in red. It's particularly good for finding variations in letterpress text, less useful for dense imagery like this. For images like this, I favor the comp tool. No, excuse me, no, I don't. I favor the overlap tool. And I'm going to go ahead and make these images a bit bigger so you can see more clearly. Okay, so the overlap tool gives me the ability to, among other things, toggle backwards and forwards between 2 images overlapped. I also have a zoom tool, a magnifying glass through which I can look at details, and you can see here signs of the engraving plate having been touched up between states. And there are some other features which are described in the workshop guide and in the accompanying website from which you can download the site that I won't go into now. Moving back to my worksheet. So there's also a link here to the image comparator online demo, which I'll just quickly show you what that looks like. So you can either select images that have been preloaded on the website. Here are some that are similar to that which you've seen on the demo data earlier. There's some more modern images at the bottom here as well. So that's the web demo. Here's instructions for local demo. Traherne is rather easier to install than some of our other tools. It doesn't require Docker. Vic, however, the last tool I'm going to demonstrate, our image classification tool, does require Docker, but I've also provided some online demos that you can try. Now, for this workshop, we've provided online instances, online demos, with a subset of Villanova University Library Special Collections images. These demos will be online until next Monday at least. I'm hoping that they might be available for a little longer. Watch this space. If they stay up after Monday, 26th of April, then that's good. They won't be available forever though. Now, Vic, the online demos of Vic that we provide aren't meant for large-scale use by many people at once. So to use them, we'd like you to pick a number between 1 and 15. So I'm going to select this text here, and I'm going to replace the $ instead with a 1. You could do any number from 1 to 15. And if you find that Vic is struggling, that's probably because several people are using it at once. So I would just go back and pick another number. When you've done that, you'll find a user interface like this. There are several ways of making this collection searchable. The quickest way to find out what's in the collection is by selecting this button here, which brings up a set of labels. These are the simple labels, image titles. So you can look at any of those, but there's also a wildcard at the top of the list. If I submit that, Okay, took a second or two. You'll get a sense of the sort of materials that the data set contains. Now, if I mouse over those images, I have an option for finding similar images. So I'm going to select this one here to ask Vic to find me images that are similar to this. It retrains on the fly and finds things that are not unrelated. I can also select many images at once using this plus sign here to try to refine that further. I won't show that now, but I do want to go back and show the labeled finding functions. So there's some sample queries here, such as dog. These have been pre-learned, and the first couple of results are somewhat meaningful, others less so. And I'd really encourage you to kind of find the limits of this technology. That many image classifications are questionable. We do represent a confidence score through these green tick boxes and these yellow warning signs for things that Vic is less confident of finding. Very often the usefulness of the result will depend on the size and granularity of the training data, but also the granularity of the object itself. Objects that are ambiguous, of course, will be retrieved with less coherence than objects that are, or in the case of dogs, species, animals that are more coherent. Let me show you something, a term that this instance of Vic, for this purposes, hasn't seen before. So if I select map, now this isn't a pre-built query. In this case, Vic is grabbing images, downloading images from Google that are simply tagged as map, modern images in this case. So we've used Google as a convenient way of finding labeled images. Let's see what it comes up with. So those seem to be, certainly in the kind of top 2 rows, meaningful. And you can go in and view the training images here and refine them if you want. So that's the Vic using the online demos. We also provide other online demos of Art UK, which I showed earlier, and BL Million. This is a million 19th century book illustrations. For a local demo, instructions are here. You can use a so-called IIIF repository. Those of you familiar with IIIF, a great technology for making images available. And you can grab, simply by inputting a IIIF manifest URI, Vic will download all the images from that, link to from that manifest and make them searchable. And if I go back to my Vic user interface, you can actually see, if you click on an image itself, we provide all the metadata made available over IIIF, including a link back to the original in Villanova's own interface. So this is potentially that seems to have gotten lost there, but okay, I'll show you this image is available through Villanova. Okay, here we go. So you can see how this search interface can be a way of traversing image collections as well as making individual image collections searchable. So that concludes the independent tryout part of the workshop. If I go back to my presentation, here we were. Here's the link again to this worksheet and demo data. And the workshop concludes here, at least the online, the part that is provided by myself. If you'd like to interact with me or each other, you can get in touch with just me over email if you have any questions or problems with anything you've tried. You can also tweet me, and that might be a way of providing a more of a communal Q&A and discussion section about computer vision for book and art history. And you can also get in touch with me through my website or with the project at this URL. So thanks very much. I hope you found that interesting, potentially also useful. Very keen to hear your thoughts if you have. If not, thank you very much for bearing with me, and take care.